All right, let's work some electrochemistry problems. Now you've already got videos on balancing oxidation reduction reactions in acidic solution and in basic solution, and that practice is going to come in handy here. But the main thing that we need to look at, the main thing we need to see is that this question is simply asking what is the standard E, what is the E naught for the reaction below. This requires looking up this reaction in the tables of standard E naught values, but we have to do it by half reactions. So we're going to have to split this up into half reactions, and that's where your practice in balancing oxidation reduction reactions comes in handy because you had to split those up into half reactions. Now the assumption is that this is already balanced. It's written this way. The assumption is it's already balanced, especially if they're giving you some coefficients, but you can double check that, count the oxygens on each side, count the hydrogens on each side, etc. But the assumption is it's balanced when they're giving it to you. So what we have to do to find the E naught is we have to look up the two half reactions that are represented by this redox reaction and add the E naughts together. There is a formula that the textbook talks about where you take the reduction reaction minus the oxidation half reaction, but I don't like thinking of it this way. Let me show you how I think about it. All right, so split it up into the two half reactions. That's step number one. This is usually pretty easy, especially after you practice, because basically you're looking for similar elements on each side of the arrow. There's your arrow, and so I'm looking for the same element on both sides. Don't look for oxygens and hydrogens first, look for the other elements. So one of my half reactions is this. That's one of my half reactions, and obviously it's not balanced yet because it doesn't have the electrons written. Recall when you balance a redox reaction, after you add the electrons in, the last step is to add the half reactions back together so that the electrons cancel. Well, this is showing the electrons already canceled, so I need to add my electrons back in. We're working those problems backwards essentially, but they're already balanced for us. So there's one of my half reactions. Now, if you'd started on the other guy, the other half reaction, you might have said, well, that's MnO4 minus and MnO2. So there's my other half reaction. But you'll notice the oxygens aren't balanced. So that leads me to look for other things in the reaction that go with this half reaction to balance it. So I need 2 waters on this side, and I need 4 OH minuses on this side to get it balanced. I also think of the charges to balance, to put those electrons back in. On the right-hand side, it's a -4. On the left-hand side, it's a -1. And therefore I need 3 electrons on this side to balance it. Again, hopefully you've been practicing that, and you will see that the electrons are balanced. Again, that's the assumption starting off the bat that it is balanced, but you can confirm that, you can double check it. So these are 2 half reactions, each with a transfer of 3 electrons. They're on opposite sides. When I add them back together, I get that balanced reaction that was asked for in the problem. Now, the next thing I want to do is I want to go look for these 2 half reactions. Now, recall this one was a little tricky, and if I had only gotten as far as this and then I didn't know what to do with the waters and the hydroxides, notice what happens when I go to look at my table. I'm looking for manganese. This is my table of standard electrode potentials, and I'm going to scroll down to manganese. It's alphabetical pretty much. Notice in these, and can I write on this? Ooh, I can write on this. Look at this. Notice in these, when I look at those manganese reactions, I'm looking, remember what I was looking for. Let me pull it back up. MnO2 and MnO4 minus. This is the half reaction that has those two. This is the only one that matches the half reaction. This is the only one that matches the reaction I was originally given. There are the other things that go with it, which is exactly the conclusion I came to looking at that original. So I've got some help here to be able to pull out and massage that half reaction. And you'll notice here that the E naught, that is the E naught for this half reaction, is 0.558. So let me go back to, let me do it this way, and write 0.558 volts, and it was written in this direction. Ooh, no, it wasn't. Let's double check that. It was not written in this direction. I don't know if there's an easier way to do this. Oh, shoot. I lost it. The MnO4 minus was first going to MnO2. It's backwards. It is exactly backwards from the way my problem lists it, which means it's not positive 0.558 I need to list, it's negative 0.558. So let's go back to here, oops, and say that written this way, it is negative 0.558. So I'm grabbing the numerical value for the E naught for the half reaction for each of my two half reactions. Now I'm going to go look for my gold. My 3Au yields 3Au plus 3 electrons. Now I'm going to go look for it in my table. All right. So scroll up to gold. Be at the top. All right. And there I see. Let's see. Now be careful because there's a couple here. This one has the 3 plus, this has the +1. I need the one with the +1. That's again based on my original reaction, and it's Au plus going to Au solid with a plus 1.692. Let me grab it over here so that I won't forget that number, because I will forget that number. All right, so let me go back to this. So you'll notice, oh, this one's backwards too. Hang on. Did I get it wrong? Was the manganese the right direction? Let's fix that. Ah, sorry. The manganese was the correct direction if I look at that flow chart. I'm sorry. You need to catch my mistakes. When we go to look at, is that where it is? Yep. When we go to look at the manganese, I think my eyes crossed for just a minute. That could happen while you're looking at it. It's MnO4 to MnO2, and that is the direction. That is the direction we needed it. And hopefully you're not switching back and forth between screens. Hopefully you can have this up in a couple of different windows that you can see them all. So plus 0.558 because it is going in this direction. MnO4 minus to MnO2. MnO4 minus to MnO2. It is positive 0.558. And therefore our gold, go back and look at that table. I'm not going to bring it back up, but go back and look at that table for the gold, and I'm looking for the Au to Au plus, and it is backwards in the table, and therefore I'm going to record negative 1.692 volts. I will bring it back up. So I'm going to record for this guy, I'm going to record the negative 1.692 because that reaction needs to go backwards. One of them has to be listed backwards and the other has to be listed forward. If you end up with two listed forward, you've made a mistake. That's how I knew I'd made a mistake. If you end up with both of them listed backwards, you've made a mistake. Again, one of them has to be forward and one of them has to be backwards. So you will be changing the sign on one of them and then you add them together. And so if I take my calculator, watch your sign, I'm adding them together. 1.692 plus positive 0.558, and my total voltage is 2.25. Third decimal place, I should tack on a 0 there, volts. It is a positive numerical value. It is a positive numerical value for that reaction. All right. Positive means spontaneous. Doesn't tell you how fast, but a positive does mean spontaneous. Couple comments about this is when you look up the values in the table, you notice I did not round. You should use the values in our textbook tables. Don't grab the values from the internet, grab them from our textbook values, because some tables may list slightly different values. All right, these are experimental values. You may find different values either through typos or updated or whatever. So use ours. Number two, you'll notice that this reaction was actually listed singly in our tables. It was 1 AU yields 1 AU plus 1 electrons, except for it was backwards. I did not multiply the voltage by 3. You don't. That voltage associated with that half reaction is regardless of stoichiometric coefficients, because the stoichiometric coefficients are just to make it balance with the other reaction. It doesn't change the cell voltage for that half reaction. That cell voltage for the half reaction is what it is. So that's how I calculate the E naught for that reaction, for any reaction that's given. Go look up the two half reactions in the tables, change the sign on the half reaction you have to flip, and add the voltages together.